So let's dive in. So let's take it at the top and let's start with this difference between AI and machine learning. You hear these terms thrown around like Chris said, and I think everybody who presents this slide has to start with the same joke. It's been around for years. Those of you who have heard it, apologies, but I think I'm required to do it when I present the slide. And the joke goes like this. How do you tell the difference between AI and machine learning? Well, if it's developed in Python, it's machine learning. If it's developed in PowerPoint, it's AI. And of course, the reason it's funny is that in this industry, there's a lot of vaporware and slideware, and it is hard to navigate all that. So we're going to try to cut through that for you. And in fact, we're going to just clarify these terms right now. So AI, of course, stands for artificial intelligence. And the way to understand it is it's a really broad set of areas that people study. And we can sum it up as intelligence demonstrated by machines. And you'll have an intuitive sense for the use cases. When you talk to Siri and Siri understands what you're saying, it seems a little bit intelligent. When you're typing into Google Gmail and it offers you a phrase to complete your sentence, it seems a little bit intelligent. And there are all sorts of variations like that. Thing to take away from AI is it's very broad and non-specific. It covers lots of different aspects. And the criteria are, if it seems a little bit intelligent, it's likely in this broad set of areas of study. So then let's go to the machine learning side of things. It's just a subset of artificial intelligence. And the way to think about it in plain English is it's teaching machines with data. And this is what we're going to break down today. We're going to step you through it bit by bit. We're going to go through some examples so that you really understand the concepts of it. At a high level, we can think about it as showing the machine some data, and the machine's going to learn some things about that data and be able to make some recommendations or predictions based on that data. And again, we're going to step through this in really nice detail. All right, so often when people approach these introductions to machine learning, they try to cover three questions. They try to cover what is it, how does it work, and how to use it. And what we observe is often they spend a lot of time on how does it work. And our take is that's not the most valuable for non-technical audiences. I think oftentimes maybe it's more the presenter trying to show off how much they know about algorithms and terminology, and often the audience gets lost. So we're not going to spend much time on that. We think it's much more valuable to answer the first question and the last question, and in particular, for decision makers in healthcare, thinking about how to make use of it, we think is way more valuable. And so we're going to spend our time there. In particular, as in all of our sessions, we're going to avoid jargon. We're purposely going to leave out a lot of terminology so that we can give you the concepts and that you can understand them in just plain English. We're going to walk through some examples step by step. We're going to really break things down and make them simple. And then in session 3, we'll get a little more detailed and do some grade school math to calculate some metrics and talk about score thresholds and really give you the fundamentals of how you can measure model performance. All right, for today's topics, we're going to cover 3 areas. Before we get to machine learning, we're going to talk a little bit about approaches that were used before machine learning. This is going to help you mentally get ready for the challenges that machine learning solves. So we're going to go through an exercise to help you think in the way that machine learning needs to solve these kinds of problems. Then the heart of our material today is going to be understanding machine learning, or ML. And then the last topic, fundamental to machine learning, of course, is data. So we're going to talk about data sources and a little bit about labeled data and what that means and why it's so fundamental to machine learning. So let's dive in. So the first thing we're going to do is we're going to talk about approaches that were used before the advent of machine learning. And those were generally rule systems. And we're actually going to make a simple rule system together. And we're going to do this for a system to identify any ball, like a basketball, baseball. So you can imagine we're going to show the system a picture, and if it has a ball in it, it should say it's a ball, and if it doesn't, it should say it's not a ball. So let's start making rules. And we're going to do this, really simple step by step. So our first rule, no surprise, is going to be, hey, it should be round like a sphere. And we could take some examples, things like a soccer ball, a basketball, and a beach ball, and we can test our system to make sure it works. It does what we expect. Okay, so it says, yes, a soccer ball is a ball, basketball is a ball, and a beach ball is a ball. No surprise. All right, well, we can keep testing it, and maybe we'll give it a little bit more tricky example. Something like this was a little bit odd. Well, unfortunately, the way our system is written right now, it would say this is a ball. And we know that's wrong. This giant sculpture or globe shouldn't be designated as a ball. So we've got to improve our system. So how do we do it? we add more rules. So let's make another rule. Rule number 2, we're going to say a ball should not be gigantic. Now, maybe that's not a very good rule. It's a little bit vague, but for our simple thought experiment, it's fine for now. So we can take our updated rules and we can test our system again. And we can see this time the system does what we would expect it to do. And it correctly says this last thing is not a ball. Great. All right, well, let's keep testing our system. Let's give it some more examples. Okay, well, this might be a problem. That's a football. Of course, it should be a ball, but it doesn't fit our rules right now. And so as it's written right now, our system would say, no, that's not a ball, which we know is wrong. All right, well, we got to go fix our rules. Maybe we'll adjust the first one to let it something be oblong, and then great, the football is now correctly scored as a ball. Let's do one more set of examples just to kind of round this out. So let's test it on some other things. You can see where this is going. The system as written is going to consider all of these 3 things as a ball. We know that's wrong. Okay, we better go update our rules to make sure we get these right. And maybe we'll add a rule that says a ball is not a fruit. And now we can correctly classify these. Now we'll cut the experiment off here. I think you get the idea. And we can kind of summarize some observations about these types of systems, these rules-based systems. And there's a couple of big takeaways. One is that they're really hard to scale. You know, we only had 3 rules. You could imagine if we were really making a system to identify balls, how many rules we might need to handle all of the cases. The other thing we notice is that it's really brittle, meaning if we change one rule, we might have gone and incorrectly assessed a number of cases. And it's really tricky to balance those rules against each other. And that they don't handle complex cases very well. Here's a sort of corner case example. This is a ball, you fill it with water and use it in a swimming pool, but it looks like a watermelon. And so you have kind of these weird corner cases in rule systems. And we can sum up the challenges in rule systems by saying they're bad in 2 really fundamental ways. So the first is they're really expensive to build and maintain. You're writing these rules by hand. As the systems get bigger and bigger, they become really complex and cumbersome. And in the end, they're not especially accurate. Trying to eke out the last bit of accuracy gains in a rules-based system is often really challenging because you get a large number of rules that are handcrafted. And so this led to the rise of machine learning. But before we get there, let's kind of sum up visually what's going on in a rules-based system. And we can do it in a really simple way. We can say, in a rule system, you're feeding in data, like your examples that you want to test, and you're feeding in the program or the rules, and the computer then applies the rules to the data, and you get the results. You get the assessment of, in this case, whether it's a ball or it's not a ball. So what we see with machine learning is really flipping this, and we can consider that kind of traditional computer programming. Those systems have existed forever, kind of if-then logic that you build up into more complicated systems. What we see with machine learning, let's leave our same diagram up here on the top, but let's flip the model on its head. And really what we're doing is we're going to move the results that you see on the right side, the thing that came out of the system, and we're going to move that over as an input. And another word that we could use for results is answers. So we're feeding in the results or the answers now as an input. And you can see what was on the left as an input on the top. We move over to the right side. And this process of applying the data, like our examples, the results or the answers, through machine learning will produce the program, the rules, or what we commonly know as a model. So really, this is a big paradigm change. This was the breakthrough around machine learning, and we're gonna break this down step by step and really help you understand this. But it's worth kind of pausing on this slide because it's important to understand the top level concept that now we're not handcrafting the rules like we did before. We're letting the algorithms, the computation construct the rules, and we're feeding in data and answers. And so how do we sum that up? What we're really doing is we're teaching machines with data. By feeding in the data and the answers and applying a machine learning algorithm, we get a model, which is an embodiment of the rules or the program that we're going to apply. So let's actually kind of step through how we would apply that. So the first thing we need to understand is what are these answers, or the term that's often used in machine learning is labels. And so let's look at what those are. in our simple ball example, the data would be the images that contain a ball or not a ball, and the labels, again, are the answers, whether that particular image represents a ball or not a ball. And typically those would be applied by humans because we're training the system based on those labels. It's really important that they are correct. If the labels are wrong, the system is going to learn the wrong things. So we want to make sure that those are applied by humans. And we can take that, just like we saw in our top level diagram, we could take the data and the labels or the answers, and we can go through this process of training a model. And again, for our purposes today, we're going to skip exactly how that's going to work. There are lots of resources out there. If you want to learn more, you can dig into that. But for our purposes, just understanding at the conceptual level, we know that there's a process that's going to train a model. And what is the model? For our purpose, it's something that we can use to feed through new examples. So maybe we have examples that the system hasn't been trained on and hasn't seen before. And the model, we can feed those examples through, and the model will give us answers. So it'll give us predictions or scores or results that say the thing on the left is a ball and the thing on the right is not a ball. And that's our use of the model, is that we want to use it to process results that we haven't seen before. So that kind of gives you a high level picture of what we're talking about. As a quick aside, if you've ever done this, some of you may have done this when you use Google, you were actually labeling data for use in machine learning algorithms for autonomous vehicles. And in self-driving cars, it's really important that they be able to tell what part of the image or video contains a street sign so that they can take the right action. And likely what you did, if you were presented with this image, you would click 6 squares, this one, this one, this one, this one, this one, this one, and you're basically saying sign, 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 and everything else not sign. So you have applied labels to these squares of the image, and that's what Google is doing when they have humans do that exercise. So back to our example, we've done this kind of facetious ball example, but how does this apply in healthcare to, say, patient data? So let's look at a way to view this in parallel. So if those are our data and our labels for our simple ball example, what does it look like for patients? Well, our data would be data about the patients, and we'll break this down in just a minute. And our labels are something that we're interested in predicting and that happened in the past. In this example, maybe we're interested in predicting cardiovascular surgery and which patients may be candidates for that surgery. So we can label historical data to say patient 101 did not have cardiovascular surgery, patient 102 did, and so on and so forth. And by applying these labels, now we're laying the foundation from the data side to be able to train machine learning models. Now let's go a little bit deeper and talk a little bit about, well, what's the data? When we have an image for our simple ball system, you might know that images are made up of pixels, which form a grid, and each pixel has a certain color that you can represent by a number, and you kind of understand what the image data is. But what is the equivalent for patients? When we talk about patient data, particularly out of EMR systems, we're talking about all that rich data that lives in EMR. So this could be encounters, which include their past interactions with physicians. It might include procedures and diagnosis codes. Other areas like labs would have lab analyte results and values for things like glucose levels and EGFR. Vitals will cover BMI and pulse ox and things like that. And meds would have prescriptions. So really rich data is available to us in the healthcare world, especially coming out of EMR. So that's what we're talking about when we're talking about the patient data that could be available to train models on. So let's summarize this, not with our simple ball example, but with our healthcare patient example. And you'll see we start, just like we did with the ball example, we start with our data and our labels. Those form the inputs to our system. In this case, we're just going to carry through our cardiovascular surgery example. We're going to train a model. And again, why do we care about the model? Because we can use it to make predictions on new patients that we haven't seen. So we can take new patients, feed that through the trained model, and we can get predictions or results out. And in this case, we say the patient on the left, patient 457, is a good candidate for cardiovascular surgery, and patient 923 is not. And again, if we go back to our really simple diagram, just 2 inputs conceptually, computation, and 1 output in the form of a model, this is what we're talking about. So I hope, I'm going to pause right here and let this sink in a little bit. I hope at the conceptual level that you get an idea about what we're talking about with machine learning and teaching machines with data, how we set up our data and our labels, and how that forms the basis for training models that we can then go use to make predictions. Now, this is not just hypothetical. I want to talk about a real example to kind of bring this back to something concrete. So cardiovascular surgery model is something that we happen to work on at Symphony RM. When we train a model, we produce some artifacts around that model to help our clients understand things like the model performance. So our system generates data sheets in the form of PDFs that explain a bit about what the model's doing, some of the data stats that the model was trained on, recommended results for good candidates. We help clients understand how that model performs, and if you use scores in the top decile or top 10%, what kind of performance you would have over kind of targeting your average patient in your population. And then one thing I'm really proud of that we've done great work, and Chris has been a great leader for us, is scoring these models not only on performance, but on potential bias and fairness. And so we give clients insights into model performance by race or ethnicity and recommend mitigation strategies where appropriate, so you can help serve your underserved groups and avoid baking bias and kind of furthering some of the bias that's embedded in much of the data sets. And then last but not least, I wanted to show a little bit about how this really gets embodied into campaigns and content. So here's an example email that would go out as a result of using our cardiovascular surgery model. And what I want you to take away is, if we look at some of the wording, you know, it's not scary at all to the consumer. It's very generic. It's not saying we're worried that you're going to have a heart attack next month. It's things like, hey, heart disease kills 1 in every 4 men. You can do things to improve your lifestyle. We've got a really simple quiz in the form of a HRA that's easy to access online. For our clients, we can talk a little bit about how good their programs are and surgical centers are with great outcomes, and make it easy to book an appointment. And so the takeaway from this is something that you can get started with quickly. It's not something that really needs to be embedded inside your clinical workflow. It's not something where we're recommending activities to physicians. This is something that helps you be proactive, drive outreach, engage with your patient population, and really use the smarts of the model in a way that's much more targeted, so that you're sending out messaging that's relevant, you're driving that proactivity and engaging your patients. So that's our quick content for today. Let's kind of break down the things that we saw. So we did our simple exercise, creating rules for our simple system to identify a ball, to kind of understand how rules-based systems work before machine learning. Then we talked a bunch about how machine learning works conceptually. We talked about teaching machines with data. And then lastly, we looked at data sources and labeled data, which is so critical for machine learning algorithms. And we think about that in terms of providing the answers that we can show the machine, so that the machine can learn the right patterns or rules and bake that into a model. Now, I wanted to go back. For those of you who were with us in session 1, we talked about our AI strategy process. We sent you all a takeaway PDF where we describe this. And this was our top level diagram for the process. And if you remember when we talked about that last week, we said there was one missing piece of the puzzle that you didn't necessarily understand after session 1, but you should understand today. So I'm going to talk a little bit about that. So last time, when we talked about step 3 and identifying data sources that are going to support that, the predictions that you want to make, you didn't necessarily have the background to understand how machine learning goes from data sources to predictions. So I hope after today's session, you now have a little bit of a sense for how that goes. You can get a sense for what kind of data you might need to be able to train models. You might have a sense for how the labels would apply. You can probably think a little bit about whether my data sources are already labeled or whether I need humans to go and apply labels. And maybe as a quick example, something like a no-show model that is predicting the likelihood of patients to no-show, where you know from your historical appointment data which patients showed up to appointments and which ones didn't. And in that case, the labels are inherent to the data. That's already labeled. Other cases where maybe you have to assess patients for whether they fit certain criteria with domain expertise or clinical knowledge, you'd want humans to apply those labels. But I hope now you can better piece together how data sources support the predictions that you want to make to achieve your objectives. So with that really ends our content for today. So I know we've got some time left. So Chris, I'd say let's open it up for questions.
Sure thing. And we have a couple of questions that we can focus on. Again, appreciate everybody coming here, and we just have time for a couple of questions, and then we'll talk about next steps, what we'll be focusing on the next conversation. But Joe, when we talk about like learning from data and these various data sources, what about if my organization doesn't have the manpower to put all that stuff together and feed it data? What are some considerations on how to be able to achieve those kinds of results or get all that stuff together?
Yeah, that's a great question. And it kind of goes back to some topics we talked a bit about in session 1 in terms of in this world of AI and machine learning, it's not just about the model training where your cost and your effort comes. Often it's around the data aggregation and collection and data prep to get all that data unified and ready to go so that data scientists can train models on it. And one thing we talked about was a lot of the investment in terms of venture capital dollars are coming in to vendors that are dramatically reducing those costs. And so as a strategist in healthcare, you want to think about, how do I maximize my use of all that investment? How do I divide the line between what my team needs to do and maybe what a trusted partner can do for me? And there's good news here. I think you can dramatically reduce a lot of those costs by working with trusted partners who can ingest a variety of data sources, maybe have pre-built ingestion pipelines, have pre-built data science pipelines. They can really cut those costs dramatically and speed your time to ROI by shifting a lot of that, where you can just give them access to raw data, and they've got the plumbing and the pipes to not only ingest that data, clean it up, unify it, and then train machine learning models on your own data that you can then go put into practice, make predictions, target audiences based on those machine learning model scores.
Thank you. And the next one really is, I mean, the idea, learning from data, then making some decisions from that looks great. But how do we actually know it's going to perform well, or how do we know it's going to accurately identify? Because I could anticipate getting some kickback if we're not outperforming our previous approach.
Yeah, it's another great topic. It's a big one, and we're going to go into lots more detail in session 3 to really arm the audience with ways to evaluate models. But I think for our purposes, we can say this. I think unfortunately the industry has had a history of really being a black box. Sometimes you hear the phrase secret sauce, where vendors just aren't willing to give you visibility or insight into how models are performing, what aspects of the data they're using. And we really haven't seen a focus on fairness and bias issues. I think what we've been really focused on is bringing that visibility and insight, being fully transparent with our clients, helping them understand the entire process, and giving them visibility into the model performance in terms of what kind of performance can they expect, how well do the models do, what kind of thresholds can they use to target very high scoring patients if they want to have a more targeted campaign, or dropping thresholds to have a broader based campaign to achieve their objectives, and then giving them insight into fairness and bias issues, and also offering them some mitigation strategies. So great, maybe a certain data set has a bias embedded in it, but you don't want to stop there. You want to have ways to outreach to some of your underserved groups and really giving them options and working to form their strategy alongside them.
Thank you. And unfortunately, we don't have time for more questions, but there's some next steps Joe's going to go over.
Yeah, so let's talk about next in our series. We're going to take a break for Thanksgiving, and then we'll be back here 2 weeks from today to cover session 3, where we go in the most detail of our entire series. And we're going to arm you with how to understand model performance. So when we talk about metrics like precision and recall and false positives and false negatives, we're going to explain this in really simple terms, in ways that everybody can understand. So you're really armed with being able to understand how models perform, and you can ask the right questions. And then of course in session 4, we bring it back to the practical And we're going to talk about some ways that you can get started that are easy and how to navigate this potentially confusing landscape.
Thank you very much, Joe. Thank you for everybody who attended. And Joe, I can't think of a more exciting way for you to tell everybody that they're going to walk into a statistics lesson. So really appreciate everybody staying on with us for this, and we will see you after the break.